Hello everyone, and welcome to TLE Eliminators PCD for Leetcode's Weekly Contest 470. Today we'll be discussing all the problems from A to D. How was the contest? Solved only one problem. Okay, no matter. It's fine. I think today C and D were a bit on the harder side, or like decently hard. A and B were doable, pretty doable. But okay, let's get into the solutions. Hello Pradeep, how was the contest for you? Yeah. So before we get started. Um, TLE Eliminators has 4 levels of competitive programming courses, which are completely self-paced, and each level corresponds to a different step in your CP journey. So if you're a complete beginner, level 1 is for you, or maybe if you're at a higher level and you need to learn things like dynamic programming, graphs, etc., then level 4 is for you. And we have everything in between as well. Each level has more than 40 hours of recorded lectures, more than 100 curated practice problems, hints and video solutions for all the problems, as well as doubt support. So for people who, feel like they're stuck or they don't know which direction they should organize their competitive programming journey in, do check out the courses. All right. Solve 2, solve 3. Yeah, interesting. Okay, yeah, 2, 2, 3, I understand, yes. Fourth was a bit high level, it was digit DP. But yeah, 1, 2, 3, I get, yeah. Okay, so let's dive right into the problems. Let's begin. Problem A, compute alternating sum. So this is a pretty straightforward problem. I don't think there's much to discuss. Um, Given an integer array, find the alternating sum of the array, which basically means all the even positions you have to add and all the odd positions you need to subtract, right? So nums of 0 minus nums of 1 plus nums of 2, so on, return the alternating sum. So I hope this is pretty straightforward for everyone. And also goes up to 100. The numbers themselves go up to 100, so they won't overflow at any point, right? So we don't need to care about overflow as well. So we can simply write problem A. We can have a very simple solution. So the first one needs to be added and the second one needs to be subtracted. The third one needs to be added and so on, right? So we can have a final sum variable like this, right? And we can have a variable which decides whether we have to add or subtract. Okay. So let's call this mul. Fine. This will be a variable which decides whether we have to add or subtract. So for each element um, in our array, for each element in our array, we need to add that to the sum. We need to add that to the sum and also multiply it with this mul, right? So if mul is +1, it will be added. If mul is -1, it will be subtracted, right? And then for the next variable, we need to change the type of mul. So plus should become minus and minus should become plus. So we can multiply with -1, right? So this is the way I implemented it. Obviously, you can implement it in many different ways. And then finally, we'll get the final sum. And so that's how we can calculate it. So yeah, let's have a look at the code. So obviously, you can do another way. You can write a for loop from I to n, and then if I is even, you can add, and if I is odd, you can subtract. So that's also works. Anyway, works. And um, yeah. So this is the code. Just go through it if you had an issue. I think no one would have issues with this one, right? No issues. Time complexity for this is simply big O of n, right? There could not be any other time complexity possible. So time complexity is big O of n. Okay, let's move on to problem B, right? I think problem A everyone would have gotten. So problem B. Is Leetcode enough for DSA OA rounds, or do we need code forces? Depends on which OA round, right? Some OA rounds tend to be very classic questions. In fact, a lot of them. But if some OAs ask out of the box questions, for that you might want to do code forces as well. Okay, let's move on to the second question. Second question was DP. Yeah, second question was pretty, just two cases actually. Um, yeah, Pradeep is correct, but let's discuss it in detail. So problem B, um, we are given an integer array. Return the length of longest subsequence whose bitwise XOR is non-zero. If there is no such subsequence, return 0. And then um, we're given, for example, an array and we have to return the length of the longest one, which is non-zero, right? So for example, in the case of 1, 2, 3, right? In the case of 1, 2, 3, what is the longest subsequence which is non-zero? Um, if you take XOR of all of them, you can take XOR of 1 and basically 1 XOR 2 XOR 3, right? What is this value? Is equal to 1 and XORed with 2 XORed with 3, right? So this becomes 0, this becomes 0, this becomes 0, right? So we cannot take the whole array, right? We cannot take the whole array as the subsequence if um its XOR is non-zero, right? But it should be pretty obvious that if its XOR is 0. But if it is non-zero, then it should be pretty obvious that we should just take the whole array, right? If XOR of all elements is non-zero, then we can just take we can just take all the elements, right? So in this case, our answer would be n. Our answer would be equal to n, right? Now, if we cannot take the whole array, we can't. Yeah, if we cannot take the whole array, right? So in this case, then what can we do? So for example, we have that example like 1, 2, 3, right? We cannot take the whole array because the XOR of the whole array is 0. So for that, we can simply exclude one element, right? For that, we can simply exclude one element. So for example, we take 1, 2, exclude 3, or take 2, 3, exclude 1, something like that, right? Or 1, 3 and exclude 2. Anyway works. So for this case, the answer would be n minus 1, right? Because if the XOR of the whole array, all of the elements is 0, then if we remove any positive element, remove any element greater than 0, then XOR becomes non-zero, right? This should be obvious. XOR becomes non-zero because the way XOR works is it counts whether basically number of bits is odd or even, right? So for example, when we have some numbers, let's say these are our numbers, okay? Let's say these are our numbers, right? As you can see, that XOR is 0 because all these bits are even, right? This bit is even number of times, this bit is even number of times, this bit is even number of times. So the XOR of this set is 0, right? But as soon as we remove one of these numbers, right, this bit becomes odd, this bit becomes odd, right? Odd number of times. It occurs odd number of times as soon as we remove this one number. That's why the answer is always n minus 1 for this case, right? If we can remove one number and we can get n minus 1. Now the only edge case, we can write it down, edge case, if the whole array is zeros, if the whole array is all zeros, right? So for example, we have an edge case like 0, 0, 0, 0, 0, right? So in this case, the answer will be 0, right? Because there is no possible subsequence we can choose, right? There is no possible subsequence we can choose. That's why the answer will be 0 in this case, right? So basically, what did we get? We got three cases, right? Summary, summary, three cases. Um, if all elements are zero, return zero. Otherwise, else, if XOR of all elements is zero, return n minus one. Else, return n. Right? So this is our solution using some straightforward observations on bits. So does that make sense? How you got the idea? The idea is simple, right? Because look, if we want to make the longest subsequence, so first thing we should think of is just using the whole array, right? First thing we should think of is just using the whole array. If we cannot use the whole array, that means that the XOR is zero of the whole array. That means we can just simply remove one number, right? So it's not exactly idea, it's just familiarity with how XOR works, that's all. Right? If the whole array has XOR is zero, then if you remove any positive number, the XOR will become non-zero, right? So that's why the answer is always n or n minus one. And only in this edge case, the answer will be zero. Right? So I hope this is clear for everyone. Let's have a look at the code. Yeah. So here the code, n is the size, xx equals the XOR of all elements. Okay. Xx equals XOR of all elements. That's what I'm doing here. And R equals OR of all elements. Okay. You don't need to take OR of all elements. You can also use if else type of thing, but you can use a Boolean flag, right? But here I'm just doing that. So basically I'm taking XOR of all elements. I'm taking OR of all elements. Okay. So now if the OR of all elements is zero, right? OR of all elements is zero. That means all elements are zero. So it's case one, and I'm doing return zero, correct? Now, if the XOR of all elements is zero, if XOR of all elements is zero, then I'm returning n minus one. Else, return n, right? So that's all the code for this. Let's have a look through it. So n is the size of nums. X will store the XOR of all elements, as you can see. For each element, I'm doing XOR with that, as well as OR with that for R. And then if OR of all elements is zero, that means all elements are zero. So we just return zero. Otherwise, if XOR is zero, then n minus minus, because we need n minus one, and you can return that value. Right? Is this clear for everyone? Okay. Should we move on to the third problem, guys? Just put on the chat. If anyone has doubt, please ask. All right. All right. So third problem gets a bit tricky, and my implementation is not the best implementation, so please excuse me. I implemented during the contest, right? So it's I think a bit longer than required, but still, uh, it's still I hope understandable. Anyways, let's go through the question. You are given a string S consisting of left opening bracket and right closing bracket, basically. So opening brackets and closing brackets, and an integer k. It is a string is k balanced if it is exactly k opening brackets followed by k closing brackets. Okay. So they've given example for k equals 3. So as you can see, k equals 3 means k opening brackets and k closing brackets. You must repeatedly remove all the non-overlapping k balanced substrings from S and then join the remaining parts. So we need to continue this process until no k balanced substring exists, right? So basically what we need to do is we need to find k balanced substrings and we need to repeatedly remove them, right? Until all the removals are done, and then we have to return the final string. Okay. So for example here k is equal to 1. So the first thing we remove is this, right? This is the only k balanced substring. Then we get this string, we remove this, and we get a final string which is empty. Okay. In this case again k is equal to 1. When we remove this, we get this, and that's the only thing. We can't remove anymore. Now here's the final example. K is equal to 3. We remove this, and then we're left with this, and there's no more k balance strings. So we stop, right? I also saw someone do hashing on this, and it worked for them as well. Someone successfully solved this with hash. Um, but yeah, I will tell you the more simple approach, suffix approach. That's interesting. I did not do suffix approach. I did an approach with stacks. All right. So yeah, let's discuss it. So first we'll solve the problem for k equals 1. Okay, we'll solve for k equals, okay, to get an idea. Fine. So in k equals 1, all we have to do is we have to remove all the patterns which are like this, right? This is k equals 1 balanced k balanced string, right? K balanced string is this, right? For k equals 1. For k equals 1, right? So let's imagine a stack approach. Okay. So stack idea, right? So we have, let's say we get some input strings. So we'll put them on the stack and we'll compare the top of the stack with the next value and we'll do it. Okay. So the stack will be initially empty, right? And then let's say we get a opening bracket. So we'll put an opening bracket on the stack like this, right? And do nothing so far. Then let's say we get another opening bracket. Let's say our string is this one. Okay. For k equals 1. Then we get another opening bracket and the opening bracket goes on top, right? And then finally we get a closing bracket, right? Now, I'm sure you have done this problem before, right? For k equals 1, you have definitely done this problem before. Standard like stack question. Then you get a closing bracket, right? Now, when you see that you have to insert a closing bracket and the previous element was opening bracket, we can just pop these two, right? We can pop these two. So we pop these two, and so these two have been popped from the stack. Now, again, we get a closing bracket, right? Again, we get a closing bracket. So when we put the closing bracket here, we see that there's an opening closing. So we can again pop these two, right? We can again pop these two. And now we are left with an empty stack, right? And so our answer is going to be an empty string, right? So what if it was a, instead of a closing bracket, it was an opening bracket here, right? So then we would add an opening bracket, add an opening bracket. A closing bracket would come and pop these two. So these two would get popped and then again would add an opening bracket, right? So something like this would be our final result. And then we could print this string. So we need to reverse the stack and then we can print the string, right? So for k equals 1, is it clear? Yeah. So for k equals 1, I think it's pretty clear, I think, right? So yeah, valid parenthesis type of question it is. Now, how do we do for k equals k, right? So like k equals greater than 1, how will we solve this using the stack idea, right? So the issue with k equals larger numbers is that basically, let's say if we had k equals 2, right? Let's say we had, or maybe we had k equals 3 and our input was something like, uh, something like this. Okay, this was our input. Then we put an opening, we put a closing. We don't pop them because we can only pop when we have 3 openings followed by 3 closings, right? So opening, 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 closing, 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 And now we see that there are three opening values, right? Followed by three closing values here and here, right? So then we can pop all of these, right? But the issue with with this approach is that we need to check we need to check the top k elements of a stack, elements of the stack at each insertion. Okay, at each insertion. Why do we need to check top k? To make sure whether we need to pop or not, right? If we naively implement this, we need to check the top k elements to find out whether we need to pop or not. So that means that the time complexity of of naive stack approach will be big of n times k, right? Because each time when we're inserting, we're checking the top k elements, then only we're inserting. So total n times k will be the time complexity. And k goes up to n by 2, right? K goes up to n by 2. As you can see, n goes up to 10 power 5. So then this goes up to roughly big O of n squared, right? So this approach will not work, or at least it will not work directly. We need to somehow optimize the time for this, right? So anyone getting an idea how to solve this? You need to check 2k elements, right? You cannot check that many elements. Oh yeah, top 2k elements, sorry. Not just k elements, yeah, top 2k elements. Right. So that's even worse. I mean, time complexity wise is the same anyways. So anyone getting an idea how to optimize this? Yeah, that's quite correct, Utkarsh. So the way we are going to do it is we're going to do what is called compression. Okay. We're going to do something which I'm not sure if this is the formal name, but that's what I've heard people call it. We're going to compress the string, right? Um, and I'll tell you what this means. Basically, we're going to compress the values on the stack to have one character followed by a integer. Okay, so it will be a pair of character and integer, and that's what we're going to push on the stack. Okay, so basically, let us take the input string. Okay, let us take the input string. The input string looks like this. Okay, this is the input string. So if you convert the string into this compressed form, what will it look like? It will look like a vector of pairs. Each pair will be something like this. Okay, each pair will be like um the character. So the character will be like this opening comma 1. Why comma 1? Because there's one opening bracket right now. Then it will be closing comma 1, right? And then it will be opening comma 3. Okay, and then it will be closing comma 3, closing comma 3. And then we'll have again opening comma 1 and closing comma 1. Okay, so this will be our compressed representation. Fine. And basically what this representation is doing is it's saying that like here there are multiple opening brackets together, right? There are three opening brackets together, three opening brackets together. So instead of writing them three times, we will just write opening bracket comma 3. Okay, so that this is the symbol and this is the count of the symbol. Okay, this is the count of the symbol, right? So now what we can do is basically um, when we push on top of our stack, right? We're pushing on top of our stack. So let's say we pushed this value right? We push this value, opening 1, then we pushed closing 1, right? Then we pushed opening 3. Now when we push closing 3, we will see that there is three opening brackets as well, right? When we push 3 closing brackets, we see that there are 3 opening brackets as well. So then we can pop these 2, right? And then we can continue on. So for example, I'll show you what happens to our stack is, um, so few things you need to keep in mind. This stack will be slightly different. So for example, if you have 5 opening brackets, okay, followed by, let's say 10 closing brackets, right? And your k is equal to 3, then how many will you pop, right? How many will you pop? So basically the situation is something like this: opening, 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 closing, 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 and then 10 total closing brackets, right? So something like this is the situation. So since k is equal to 3, we can only pop one group over here, right? We can only pop one group here. So when we insert the closing brackets, we will see that how many groups we can take, groups of 3 from this and groups of 3 from this. So basically, let's say this is count 2, count 1. So min of count 1, comma count 2 divided by k. Okay. So these are the number of groups formed, right? We are taking minimum of 10 and 5 and dividing by 3. So that is 5 divided by 3. That means we can get one group of size 3, correct? One group of size 3, which we can form like this, and we can pop it out. And how do we pop it out? We can simply minus 3 from both of these, right? We can minus 3 from both of these. So this will become 7, and then this will become 2, okay? And then when we insert more, let's say we inserted some more closing brackets, okay? Let's say we inserted some more closing brackets, like we inserted 5 closing brackets more. Fine. So then instead of adding it on top on the stack, since this is also closing bracket and this is also the closing bracket, same symbol, they have the same symbol, right? They have the same symbol. What we'll do is we'll simply add these two and it will become 12, right? And so this is what our stack will look like. So the next time something comes on the stack, it will be a different symbol itself, right? And then we can compare them. We can remove groups of 3. So this becomes 1, and this will become 9, and then we can keep adding and continuing this process. Okay. And so once the stack is done, once the stack has finished, right? So it's basically the same process, basically the same process as above, the same process as before, but with this compressed values, with this compressed values, right? Yeah. So let's also iron out some details. So let's just write the steps down neatly. Okay. So steps. First step is compress the values of input string, right? Compress the values of input string. Let's write down the steps in a neat manner. Okay. Create a stack of pair. Okay. 3. Add each compressed value to the stack, one by one. Okay. And after adding it, so this will put it in 3.1, right? 3.1. After adding, what you do is you have to compare the top 2 elements of the stack. Okay. So while stack.size is greater than equal to the top 2 elements, compare top 2 elements. If same symbol, if they are the same symbol, then merge them, right? Merge them into one symbol. Then just add the values, just combine the values. I guess you can say there'll be only one element then, right? Same symbol means both are opening, so we can just combine the values, right? If there are different symbol, if they are So if they are different symbol and they have to be opening followed by closing, right? So if they are different and opening followed by closing, opening followed by closing, then check how many k can be removed, how many k can be removed from both of them, right? Can be removed. Basically divide by k for both of their counts and do it. If one of them becomes zero, then we have to just pop that element, right? If any element is zero, do not add it back. Right? If they are closing followed by opening, then we cannot do anything. If they are closing followed by opening, then we can just break. We cannot do anything in that case. So break. Okay. So this is the cases we have, and we run this while loop, and then we add the next compressed value, and again we run this while loop while the top two elements of the stack. We compare them and we check if what type they are. We do the process, right? And we repeat this until all the values are compressed. Okay, so this is going to be our idea. And then finally, 5, create answer string, or 4, I guess, answer string, insert all elements of stack in reverse, insert, decompress it. Decompress means simply the number of count for the symbol we should put, the elements of stack in reverse, right? Because the stack will reverse them, so we need to reverse it again in reverse order. Return final string, right? Return answer string. Okay, so this is basically the idea. We're using stacks and compression. Compress the value of the initial string. How much time will this take? Big O of n, right? Big O of n is length of string. Create a stack of pairs. That's big O of 1. We add each compressed value to the stack, and we compare the top two and pop. If you observe, this is also big O of n itself, because at most we're comparing two values at a time, right? So at most it's 2n, which is big O of n itself, right? We're only ever comparing the top two elements. Then decompression is also big O of n. So the final time complexity of this solution is also big O of n, right? So I hope that's understandable. By compressing the values, creating stack of pairs, adding the compressed values, we have to do some cases, right? So compare the top two elements, we have some cases. If they're the same symbol, we just merge them. If they're different symbol and they're opening closing type of symbols, then we can count how many k to pop away. And otherwise, if they're closing opening, then we can just break. Then we find the answer and we return it, right? So is this, yeah, at last we return the remaining string. So I think, is this clear? Is this clear? So one note I tell you, so my code is what I wrote in the contest, so it was not that neat. But yeah, one note before you try to understand my, I wrote opening brackets, and I wrote closing bracket symbol as -1. So it will look like +1 and the count like 10, and my closing brackets will look like -1 and 9, something like this. Okay, so that's how I have done my implementation. That's the only thing. Otherwise, the implementation is pretty similar to what I wrote. Okay, note regarding my code. I don't think it changes what symbol you use, right? So that's why I did it that way. Okay, so let's have a look at the code now. Yeah. Okay, so here we are having the counts of each element. Okay, so counts basically means, so counts of opening followed by closing, etc. Okay, so basically what it's doing is, if the current element is equal to the previous element, it will increase the count. Otherwise, it will add a new count. Okay, so basically, it's going to take a string like this. It's going to take a string which looks like this, right? And it's going to convert it to, this is 3 elements, so it will be 3, comma 2 elements, so it's going to be 2, 1, 1, 2, 3. Okay, so this is what I'm storing in my array counts. Okay, so basically, if the first one is an opening element, then that means second one is count of closing, opening count, closing count, opening count, closing count, right? So I'm not storing the pairs over here. I'm just storing the counts for now. So yeah, the implementation could have been neater, but yeah, that's how I've implemented it. So I'm storing the counts here. Then I have stack of pair int comma int, and type is going to be my +1 or -1. +1 means opening, -1 means closing. Okay, so that's how I'm going to store my values in my stack. So for each element in my counts, I will push the type and the element. Okay, I'll push the type and the element. If the first one's type is +1, then the second one's type must be -1, right? Similarly, if the second one's type is first one's type is -1, the second one's type must be +1. So that's why I'm multiplying with -1 over here, right? So this is just making sure the types will alternate when I'm pushing. That's all, right? So opening followed by closing followed by opening, so on. That's what the counts will have. That's why I'm taking each element of count and I'm pushing type comma that X element. Okay. Now here is the main core logic, which is our while loop, right? So far we did step 1, step 2, and step 3. Now we're going to discuss this step 3.1, which is the main logic, which is as long as the stack has size greater than equal to 2, right? We are popping the topmost two elements, right? We're popping the topmost two elements. We have their type as well as the count, or type as well as the value for both of the elements. If they are equal, then we can just push the symbol and the sum of the counts and continue, right? If they are not equal, and the second one is not a closing bracket. Okay, so second one is not a closing bracket, right? That means that it is not of the this form, right? Not of the opening and closing form. Then we can simply push them back and break, right? So this is the case over here, right? If they are different, then we can simply break. So that is this case. If it is closing followed by opening, simply break. So that is the case. This case, okay? Case 2. This is the case 1. This is the case 1. Now we're coming to this case, the middle case, which is case 3. Okay. So in this case, what do we do? This is the remaining. So this is how many k balanced we can form, right? So I'm taking AVBV divided by k, right? So min of the length of A, the opening brackets, comma the length of B, the closing brackets, and I'm dividing by k, right? Now I'm subtracting both of them by k. If they are not equal to 0, so if the value is not equal to 0, I will push them back, right? If the value is not equal to 0, I'll push them back. Also, if I did no change, like if V was 0, I need to break, otherwise I will be stuck in infinite loop, right? So if I made no changes, then I must break, else I will be in an infinite loop, right? I will be in infinite in infinite loop. So this is just to break if I made no changes, okay? So what I'm doing is I'm finding how many I can remove. I'm subtracting them. Then I'm pushing them back if they're greater than equal to 0, obviously. If otherwise, there's no point pushing them back, right? So if they're greater than equal to 0, I push them back. If I made no changes, I will break because I don't want to go into infinite loop, right? So this is the basically the stack thing itself, but we are comparing the values here, right? We're comparing the values instead of directly subtracting by 1. Okay, so now our stack is ready. We need to find the answer. We create an answer string for each element of stack. We find its type and the count. We push back that value. So if type is 1, it's an opening bracket. Otherwise, it's a closing bracket. We push it back x times, okay, or the number of count times. Then we reverse the whole string and return the answer. So that's all. If you're familiar with this compression idea, it's pretty straightforward question, right? Is there some issue with the mic? Pradeep, what is your question? Why can't we push the substring of same symbol and then do this check? I don't know what that. What are you asking exactly? Can you elaborate? Okay, okay. Can we do this problem using KMP rather than something like pattern finding? I am not sure how to do that, but yes, I know someone who did that. One of my friends told me that they did that with KMP or some kind of hashing approach. How would you do that? I guess it is possible, yeah, because what you can do is you can hash the target string and you can repeatedly look for that hashed value in your main string. And if you find the hashed value, you can go back a few steps and look for it again. So I guess, yeah, you can solve it with KMP, but it would be a bit more complicated to code, I think. Anyways, I think this is the simplest solution, and I think this is what they intended because it's also big O of n itself. And obviously, I did not code it the most elegant way, but I think you can code it within 30, 20 lines if you write it very elegantly. All right, let's move on to problem D now. So, did anyone get problem D? It's a bit of an advanced topic. So, if it's your first time get knowing the topic, I think it'd be pretty hard to understand. But yeah, we'll move on to problem D. Okay, so let's move on to problem D. As a prerequisite, how many of you have heard of something called digit DP? I just want to know just a general idea because it is easily like at least 1900 plus on Codeforce's concept. Like I don't see it much in below 1900 questions. So at least 1900 plus on Codeforce's concept. So I'm not sure how many in the chat would know this. Just give me an idea of how many people know this, heard about it. Okay. Hmm. Right. Okay. Okay. So some people have heard of the idea, but I think you would not know how to implement it. Yeah. Okay. So I'll give you a good resource. I'm not sure if digit DP is covered in the TLE course. I don't think it is, but if you go to USECO, there is digit DP, right? Uh, so it's not much resource they have, but it's a bit dense. But yeah, you can go read on it if you are interested, and you can try some of the problems. Um, yeah. So digit DP is used to solve dynamic programming values, where we do DP on the decimal places of the numbers. Okay. So that's my basic description of digit DP. You think a lot of Leetcode 4 are digit DP? No, not really. They're usually some advanced concept or the other, Pradeep. But in I've been doing Leetcode PCD for about 3 months now, right? And this is the first time I saw digit DP question. So not always. But yeah, usually they use some or the other concept. Like sometimes it's LCA, sometimes it's this DP, sometimes it's segment tree, sparse table, something like that. So usually the fourth question does use some or the other data structure or some concept. Okay. So yeah, as a prerequisite, this question you need to know some digit DP. After this video, you can go about it, maybe rewatch it after that. But yeah, I will try to explain it now as well as the best I can. Okay. So count no zero pairs that sum to n. Okay. So a no zero integer is a positive integer that does not contain the digit 0 in its decimal representation. Okay. And we need to count given an integer n. Okay. So given an integer n, which may or may not be no zero, by the way. Um, find the number of pairs. Find the number of pairs of pairs a comma b such that a plus b is equal to n and a and b are no zero. Okay, a and b are no zero. A comma b are no zero. Okay, so they have no zeros in the decimal representation, right? So here we need to basically count what set of digits satisfy some conditions, right? So the first condition is this, and the second condition is this, right? So these are the two conditions, and we have to find a count of the number of digits which satisfy this number of numbers, pairs of numbers which satisfy this condition. Okay, so yeah, and there are some examples. So take n equals 3. N equals 3, you have two options, 1 comma 2 or 2 comma 1. Take n equals 11, you have several options like 2 comma 9, 4 comma 7, so on. Also note that 1 comma 10, 10 comma 1 will not satisfy because 10 contains a 0, correct? Now the main difficulty here is the constraint is n less than 10 to the power 15. Okay, so the main um, constraint here is n less than equal to 10 to the power 15. Okay, so we need to keep this in mind. So obviously this removes any chances, any chance of big of n solution. Our solution needs to be like big of log n, etc. Right? It can be big of log n squared. That kind of solution we need to have. Okay. So now there is not much intuition actually. So if you study digit DP, you will know that this is a very standard and straightforward question in digit DP. Like whenever you need to count the number of numbers which have their digits satisfying some conditions, like they have no zeros, or there can be conditions like it should not have a 2, it should not have a 3, it should not have a 7, or there can be conditions like 3 should appear exactly twice and never appear again, something like that. So these kinds of questions, when we need to count the numbers, all of these questions, digit DP works. Okay, so whenever we need to count the number of digits, the number of numbers, sorry, uh, the number count the numbers less than equal to n such that some conditions are imposed on the digits, right? Are imposed on the digits. So, for example, the conditions can be of the type um, some digit does not occur, right? Some digit does not occur, does not occur. So, if you take the example, like 0 does not occur in this case, right? So 0 does not occur. Or we can even have more complicated things like the digit 2 occurs exactly twice, right? So it's not there in this question, but you can have complicated conditions like this. And one more condition we have is like, for example, a plus b equals n. So that kind of condition can also be handled. It's also a condition on the digits itself. It's a condition that the digit of a and the digit of b should sum to whatever digit is there in n, right? So for example, if we have n is equal to 1015, right? And that is equal to, let's say, 700 plus 315, something like this, right? Then basically the condition which we are imposing is that, let me just write it down. So 700 plus 315, 1015, right? So the condition which is being imposed here is that whatever the two digits are there from A and B, their sum should be equal to 5. Similarly, in this position, the condition is that the sum of these two digits should be equal to 1. In this position, the condition is that the sum of these two digits should be equal to 0. And also we are going to have a carry value which will also be a DP state. The carry value moves on, and then here the sum will also 1 plus 0 will be again 1, right? So these are also some conditions on the digits. Okay, conditions on the digits. And if we need to count for large numbers like n less than 10 power 15, in fact n less than 10 power 18 will also work, right? Then we should use digit DP. Okay, so I hope I've given an understanding for where we use digit DP. All right. So now I'll explain how digit DP works. Okay, a little bit. Um, digit DP. Okay. So what we do is we start from the LSB. Okay, at least in this question, start from the LSB, right? And we will say that um, once the first I positions in the numbers uh, A and B are fixed. Okay, how many number of ways remain? Okay, how many number of ways will remain? Okay, so basically DP of I is going to store that first I digits are done, then how many number of ways remain. Okay, so DP of I basically stores first I digits are done, first I digits are fixed, how many ways remain. Okay, how many ways can we fill the other digits? Can we fill the other digits? Okay, so keep this in mind, right? And one more thing. So yeah, so what will be our base case, right? Our base case. So if all the digits are done, so let's say there are total n digits, right? So DP of n will obviously be 1. So if all the digits are done, there are no number of digits to fill remaining. So DP of n is simply 1, right? And the answer to find is DP of 0. Okay, DP of 0 means no digits are done. So no digits are fixed. Digits are fixed. How many ways to fill all digits? How many ways to fill ways? How many ways to fill all the digits? Okay, so this is basically one of our DP states, which is the position. Okay, the position I and how many are fixed basically. So I hope this is clear. Basically, our idea will be something like this. Idea will be something like this. So we know that DP of n is equal to 1, right? So then we can find DP of n minus 1 somehow using this. Then we will do some more transitions until we reach DP of 0, and that will be our answer. Okay, that makes sense. Okay, so that makes sense. That's basically an idea of digit DP. And now we also need to care about what all we can choose for a particular digit. Okay, what all we can choose for a particular digit. So let's say we are at some DP of I. Let's say let's figure out our whole state. Okay, figure out our state. Okay, let's say we are at some DP of I. Okay, we are at DP of I. Now how do we transition to I plus 1? Okay, how to transition to DP of I plus 1? Okay, so let's say that basically means that the first um, I digits of A are fixed. Okay, so some first I digits of A have already been set, and the first I digits of of B have already been set. Okay, so A is equal to this number, B is equal to this number. Now we have to set the remaining digits. Okay, now we have to set the remaining digits. So if you add them both, then it will be n. Okay, so n will also be having some values. N's values are already known, right? All the digits of n are already known. So this is the sum, right? So currently we have filled all the I digits, and what we need to do is we need to find a way to to find this count of how many ways to fill the remaining digits, right, for I plus 1. So that's the step we are at. So then, how many possible ways can we fill these two digits, right? How many possible ways can we fill these two digits? So that's obviously 10 into 10 ways, right? 10 into 10 ways. Why? Because um, this digit can be 0, this digit can be 1, this digit can be 2, 3, 4, 5, 6, 7, 8, 9, right? Similarly, this can be 0, 1, 2, all the way till 9, right? So there are total 10 ways to add next digit of A, 10 ways to add next digit of A, and 10 ways to add next digit of B. Okay, so that's where we are right now. So what is important right now, right? So now the first thing is that already these numbers are fixed. As you can see, already these numbers are fixed. So one thing which would have happened was adding these two, gave us a carry, right? Adding these two gave us a carry. So we should keep that in mind. Also, please note that this addition is being done from left to right. Okay, this is LSB to MSB because we are starting with LSB. That's why it's written ulta. So carry will go like this. Okay, so it's LSB to MSB. I've written it in ulta fashion to understand the DP. Okay, so first thing we need to know is whether there's a carry or not, because that will affect the value which is coming here, right? So if there's a carry or not, so that has to be part of our state. Okay, so part of our state, is there a carry or not? Okay, is there a carry or not? Okay, so far our state looks like this. Our state looks like this. It's going to be dp of I of C. Okay, so I is the position and C is the carry or not. Okay, carry, which and carry will be simply 0 or 1, because when we add two one digit numbers, either we get a carry of 0 or we get a carry of 1, right? Now what? Um, Now the next thing we need to know is, so next condition we need to satisfy is non-zero condition, right? Non-zero condition we need to track, right? But the interesting thing is when we add two numbers, so let's say we are trying to find the number, let's say 1000. Okay, n equals 1000, and then one valid solution is, for example, a is equal to 991, right? And b is equal to um 9, for example, right? And if you write them out fully, then if we write from, we're writing ulta, okay, we're writing left to right. So if we write them out fully, we get n is equal to 0001 a, or let's just write it properly itself. N is equal to 1000. Um, a will be equal to 0991. B will be equal to 0009, right? So the thing is, these numbers are also having zeros, so we cannot forbid zeros completely. But what we could say is that after these non-zero numbers are over, we need to stop here, and everything afterwards should be only zeros. Okay, so there is some stopping point, right? There's a stopping point in each number, and based on that stopping point, all the numbers should be zero from some point onwards or not, right? So that also needs to be added to our DP state. Okay, so one is the position, one is the carry or not, and the other thing which will tell us whether the current number what are allowed or not, right? We need to know what is allowed for the current number or not. So basically, all the numbers from 0 to 9 could be valid, but the thing is that if we have already reached the stopping point, like these were already zeros, then here also we must put only a 0. And if this was not a stopping point, then we can choose to stop or not, right? So then we need one more thing. Um, we need one more thing in our state, which is stopping of A and stopping of B. Okay, so this will also be 0 or 1, which means whether A has stopped or not and whether B has stopped or not. Okay, and yeah, that's all. This is our complete state, which is going to be the position, the carry, whether A has stopped or not, or whether B has stopped or not. Okay, based on this, we can find the count of all the next digits, and I will show you the transition. Okay, the transition. If this is all going over your head, please don't worry. Digit DP is a concept which you usually learn after you become at least expert or more than that, right? So don't worry about it. It's a slightly advanced concept. But yeah, if if you can follow along, no problems in that as well. Okay, fine. So given that we are at position I, we are at position I, and we have some carry, right? Carry is C, which is either 0 or 1, and whether we have stopped A or not. So stopped A is 0 or 1, and whether we have stopped B or not, which is also 0 or 1. Okay, now we need to find how to find this value, find this value, find this value using DP of I plus 1 values. Okay, DP of I plus 1. All right, so what we'll do is for each value of A, for each value of A from 0 to 9, correct? For this current digit. So for each state, we'll do this. For each value of A from 0 to 9, for each value of B from 0 to 9, B from 0 to 9, okay? And we will say, so first of all, if it's conflicting with SA and SB, then we can just continue, okay? Just continue, okay? And what does conflicting mean? If stop A is on, if stop A is 1, that means that it should be zeros. But if A gets some digit value like 1, then that's not allowed, right? So we will continue in that case, okay? If it does not follow, if it does not follow A plus B, right, plus carry, A plus B plus the carry, mod 10 is equal to the ith value of our number, the ith digit of our number, then also we can continue, right? Because we need that second condition that A plus B plus the carry of this digit. Mod 10 means we are just checking that column if it's not equal to the ith value, right? So if it's not equal to, we will continue. Basically, what it means is that, so here you can see that 9 plus 0 equals, yeah, and the carry is 1 over here, right? 9 plus 0, and if you add them up, you get 1, 0, right? And so this 0 matches with this 0 in our target. Sorry, the 0, the carry is over here, sorry. So the 0, when you add 9, right, and the carry will match over here. So basically, check if you add this value of A and if you value of B, will we get the ith digit? Okay, so we're making sure B equals n. Right, so sum of A, B, and carry is equal to the ith digit, correct? So if it does not follow this, we will continue. Now, if it is following this and following the previous one, then it's a valid state, right? And then what we can do is we can fill this particular value and we can say answer plus equal to dp of I plus 1, whatever the new carry is. So the new carry will be simply a plus b plus c divided by 10, right? So this will be the new carry. And then whatever the stopping value is, so stopping value of A, stopping value of B, right? So if A and B have taken the value of 0 right now, then the stopping value will be converted to 0 or 1, okay? So that's how our DP works. And we need to make sure that later values are computed first. So in my code, I just wrote it as recursive DP itself. So I wrote it as recursive DP with memoization, because for digit DP, to be honest, that's much simpler. So recursive DP with memoization only I wrote today in my code. So basically, it's something like this. It's going to be like, it's going to be a function. So let me just write it, which returns a LL. Obviously, we need the count, right? So LL f of position I, the carry value C, stopping value of A, stopping value of B, right? And if the position, if it's the base case, so first we need to check the base case. So if I equal to n, and also when you reach the n position, the carry should not be 1, okay? The carry should not be 1, and carry is not equal to 1, the carry is not equal to 1, then we return 1, right? Else, if I is equal to n, then we can return 0, because if the carry is equal to 1, then there's no way to reach the n position like this. We will return 0, okay? So this is the base case. Fine, this is the base case. Then the next thing we can check is if dp of I, C, start A, start B, if it's already stored, so if it's memoized, so we can say that if it's not processed, it will be -1. Then we can simply return this value. So this is to ensure that we're not doing exponential, we're doing a DP, right? So we're doing recursive DP with memoization basically. Yeah, so this is that case. Now we can try all the possible values of A. So for each value of A or the digit A at the ith position of A from 0 to 9. Now for each value of B from 0 to 9, value of B from 0 to 9, check if value is valid, right? Value is valid. And also check if A plus B plus carry mod 10 is equal to the nth digit, right? Sorry, the ith digit of n. Fine. So we need to check this and we need to check this. Once we're done checking both of these conditions, that means it's a valid way. So we can have a value plus equal to dp of I plus 1, which means, okay, this digit we have fixed. Now we can find the ways to fill the next digit. The carry will be A plus B plus C divided by 10, right? And the new value of stopping A, new value of stopping B. So if A has currently stopped, the new value will become 1, right? Similarly, if B has currently stopped, the new value will become 1. So yeah, we increase the value like this. And then value will be 0 over here, and we can return this value. And when returning the value, we will store this so that we don't recompute it again, right? So we'll store dp of I, carry, stopping A, stopping B is equal to this value. Okay, so we'll return this value. And this is a straightforward memoized DP, digit DP to find our answer. And what will be the time complexity of this? Okay, so first we'll see the memory complexity. Memory complexity will be simply the number of states we have. So memory complexity will be, what is our state, right? DP of I, C, SA, SB. So I is equal to, um, the maximum is 10 power 15, which means 16 digits. For safety, I just took 17 digits. So let's say 17 multiplied by, carry can be either 0 or 1. So 2. Starting, whether A has stopped or B has stopped, also has two values. So 2 into 2, right? So this is the total memory complexity. Very small, as you can see, um, almost constant or log n. So that's how much, 17 into 8, right? So roughly 136 is our memory. Like only this much memory is being used by our whole DP table. Okay, so 136 bytes, you can say. And now what is the time complexity? So each state we need to consider, right? So when we calculate the time complexity of DP, it's going to be number of states times the time taken in the transition, right? So we already know the number of states. The number of states is 136 roughly. And the time taken in transition will be 10 into 10 because we're checking 10 values of A and 10 values of B, right? So 10 into 10, which is again very small, as you can see. This is barely anything. It's just 10, like 13,000 operations, raw operations, 13,000-ish operations total. In fact, we can even go up to 20 digits, 30, 40, 50 digits without any issue for our numbers. Okay. Because the number of digits is just changing this value. That's it. So yeah, was my explanation understandable for digit DP? Can you share some more problems? Yeah. How do you calculate stopping A and stopping B? So basically, um, if my current value of A, if my current value of A is 0, then stopping new value of stopping A. So new value of stopping A, so NSA is equal to 1. Okay. And similarly, if current value of B is 0, then new value of stopping A, new value of stopping B will be 1. Okay. Add, that's basically how we calculate stopping A and stopping B. And one more thing we need to ensure is if the old stopping A is equal to 1, then current digit of A can only be 0. Okay, can only be 0, etc. So these are the rules we need to enforce. Okay. In my code, I did not write it so cleanly, but yeah, you can clean up the code a little more. Okay. N is the number of digits in N. Oh yeah, true. Might be a bit confusing in some places, but yeah, I goes up to the number of digits in n. So we can write it as I less than equal to n, which is equal to number of digits in n. So we can write like small n and capital N. Capital N is the original number and n is the number of digits in capital N. Fine. In my code, I did not write this logic of stopping A and stopping B this cleanly, but it's the same thing. I just wrote all the cases out. So I'll just show it with the code itself. Okay. So first thing, when we take our input of n, I'm finding all the digits of n and I'm storing them in a vector. Okay, because I need to know which ith digit is equal to what. I need to know that, right? So digits dot pushback temp percentage 10, and then temp is being divided by 10. Okay, and L is equal to the size of the digits. L is equal to size of digits. The entire DP is being set with -1. That means it's unprocessed so far. And I'm returning ans of 0, 0, 0, which is my base case. So 0 digits are done. The carry is 0. A has not stopped. B has not stopped. So this is my base case, which I'm returning. Okay. What are the things which I'm storing? I'm defining LL. I'm defining my DP vector. It's at most 17 into 2 into 2 into 2. These are my digits. So digits array. L is the length of the digit array. Now here's my answer. ICSASP. And yeah, this could have definitely been shortened, but please bear with it. I'll explain it's the same thing. So if I is equal to the length, so if the whole length has been reached, if the carry is 0, then and only then we return 1, otherwise we return a 0. Now, if the DP value has already been computed, if it's not equal to -1, we just return the DP value. Okay. Now value is the sum of all the possible ways for this particular DP ID, right? This is what we return at the end. We're returning the value. Now we're going to try each possible digit of A. Okay. So current digit of A is equal to this variable AA, which I've written here. Okay, so we're trying each of them from 0 to 9. Okay, we're trying each possible value from 0 to 9. This is the new value of SA, new value of stopping A. If the old stopping A was 0, and if the current digit is 0, then we are making sure that at least one non-zero digit. Okay, so this is the thing which I should have mentioned, but there should be at least one non-zero digit, correct? So if the stopping value of A is 0, and stopping value of A is 0 means it has not stopped yet. Okay, not stopped yet. Current value is 0. Current value is 0. The current digit has become 0. If I is equal to 0, then it's not a valid case. Okay, it's not a valid case. We just continue. Fine, we continue to the next possible value of A. But otherwise, we can say that now A has stopped. Now A has stopped. So new stopping value is equal to 1. Equal to 1. Okay. Similarly, if A has already stopped, then if AA is 0, then the new stopping value remains 1. Otherwise, we continue. Okay. So A has stopped. Current digit must be 0. Otherwise, continue. Okay. So this thing I've written a bit long, but yeah, the main thing you need to make sure is that we cannot stop at I equals 0, because at least one digit, the LSB, has to be non-zero, right? Otherwise, it will be complete zeros, which is not allowed. So pay attention to this line. Similarly, exact same logic for B. I just copy pasted this and changed A to B. Okay, that's all. So same thing. Stopping digit of new stopping value of B. I'm calculating it. I'm making sure that the first digit is non-zero and everything else is exactly the same. So just go through the code once. Now I'm calculating the sum. Okay, sum of this digit. So sum at this digit is equal to A digit plus B digit plus carry value, right? So I'm calculating that sum. If this sum mod 10 is not equal to the ith digit, right? So I computed this digits array in the start itself. If it's not equal to the ith digit, I will continue. Otherwise, it's a valid case, and I will do answer plus equal to I plus 1, sum divided by 10 for the carry, new stopping value of A, new stopping value of B. Okay. And finally, this is DP of I. So yeah, I hope this makes sense, right? Sometimes digit DP is done by storing all the last values. So here I just need to know whether the previous value has stopped or not. Sometimes you store all the values like um, 10 values here, 10 values here. That only changes your digit DP into like 10, 10 here. But here I just need two values, whether it has stopped or not. But yeah, many different types of digit DP can be done. So if you're trying to remove other numbers, you might have some more dimensions to your digit DP. But basically, all digit DP follow this same kind of formula where you figure out your transition by seeing what conditions your numbers have on the digits. And each digit becomes its own state. Often you have um, this carry state, and here we are just making sure that stop A and stop B are handled, right? Yeah. So as I said, the time complexity is pretty short. So you could write this as log n in a way. You could write this as log n. Memory complexity also you could write as log n. All right. So that's about it for today's questions. Um, AA and BB are nested. Yes, you are correct. AA and BB are nested. Here is AA and here is BB. So they are nested. In fact, I can take this whole thing and put the logic here itself. But yeah, I should simplify this logic. So instead of doing if else these many times, you can just find the value of NSA and NSB directly over here. And only these three cases, one, two, these two exception cases you need to handle. Fine. Okay, then. Any doubts, guys, regarding any of the questions? We have come to the end of the session now. So general doubts. Hello. Yeah, go ahead. I'll take any general doubts if you have, even related to CP or whatever, general CP if you want. If AA is 0 and I is not 0, then you're setting NSA as 1. What is I? If AA is 0 and my previous SA is not 0, then I set NSA as 1, yes. Yeah, you're correct. No, no, A cannot have digit 0 in between. Read the question again. Pradeep, the question says that your number must be a no zero integer. It cannot contain the digit 0 in between. It cannot have a digit 0 in decimal representation. That's literally the question. Count no zero numbers, which is why we're using digit DP, right? So A cannot have a digit 0 in between. It only can have digit 0 once it has stopped. That's pretty much why we're doing this whole process. Yep. The approach I've used in problem 3 is standard or general observation. I would say that it is a mix of both. I have seen this kind of question before, so I would say it's standard. Compressing is standard. But if you have never seen it before, I think with some general observation, you can still solve it. But yeah, I would say it's a bit standard, problem 3. I've seen it before. Like I've seen the exact same thing before. But I'm not sure if that's a good measure for standard or not. But yeah, once you solve like 1500 rated problems, you will see that it's a bit standard. Okay, Akash, if you're on six, like you said, you're 1700 on Leetcode, but you feel stuck, right? So first of all, if you're in the TLE course, then maybe TLE level 3 would be good for you, right? And second, I want to know like whether you have an issue with topics or whether you have an issue with practice. So for example, if you want to solve the third question, like as you can see, the third question today was stacks, right? So have you practiced questions regarding stacks? Have you practiced binary search, two pointers, combinatorics? So these are the questions which usually come, right? And graphs sometimes comes as third question. So if you're not familiar with the topics, then first you should spend 1 or 2 months learning the topics properly. That means learn the topic, do 10, 20, 30 questions per topic. Then after that, once you have learned all the topics, you can do general contests. Like that's pretty much the only way to improve. Should I do DSA or Dev? That I cannot really advise you. It depends on what your interest lies in, right? If you feel like development is your calling, then you should go for that. Um, that's a very subjective thing to ask. If zero was allowed in between, Pradeep, then we would not even need to care about having NSA, NSB. We could just continue. Like we could just remove those two things from the state. We don't care whether it's a zero or not then, right, at any position. So we might as well just continue onwards. So we can just remove the NSA, NSB conditions completely. How to improve digit DP? Because digit DP problems are very limited. Um, to be honest, yeah, the problems are limited. Like even if you look on the internet, max you'll find 5 to 10 problems. And the thing is, I feel like if you want to do good in questions like this, right? You need a baseline rating improvement. Like if you are currently, let's say 1500 on code forces, I suggest practicing normal DP and normal things first. When you come to 1700, 1800, then you can practice DP, and then I think it will stick with you because already your like reflexes have been trained to think in that way. What is the best strategy to break div to C barrier in code forces? Personally, for me, it was solving VCs and solving old div to Cs. So I had the issue that I mostly knew all the topics. I mostly knew many of the topics, right? Um, many of the topics. Like I had understood by then binary search, I had understood DP, and I had understood graphs, which are basically your main topics itself, right? Really, these things I had learned to some level. After that, what I did was I had solved. I also had been stuck at that barrier for a bit. I had solved like maybe like 50 past div to C-ish questions. Questions roughly, not too old also. It should be recent. And then I did DCs. So that's the way I did it. Obviously, it'll be different for everyone, but personally, I feel like if you do this much, you will definitely be able to solve div to Cs. It's for Arpit. All right, then, everyone. I think that's all the doubts for today. Thank you for watching. And what is my ID? You can, yeah, my ID in CF, it's Accord. It's there on the TLE website. You can check it. Accord, ACCORD. Okay. All right, then, guys. Uh, thank you for watching. Hope you learned something. Do rewatch the video and absolve the questions, right? And see you in the next stream. Bye bye.